Okay, so let's start. Today, we're going to basically talk about gambling, because what's money good for if you don't want to gamble? And the idea here is to figure out how to generate random numbers on the blockchain. So let's say I just want to do a lottery and just create a new contract. I'm going to call this one lottery.sol. And okay. So I just want to have a lottery contract. And I want this to be like a very simple kind of lottery where anyone can buy tickets. And then we want to randomly choose one of the people who bought the ticket and pay all the money to them. So let's just have a simple contract here. And things will get really complicated really soon. So let's see. So first of all, I want to have a function to buy a ticket. So first put this on auto compile. Okay. So let's say I have a function called buy tickets. Now I want anyone to be able to call this function. So I want this to be public. And you have to, of course, pay the contract to buy a ticket. So I want it to be payable. And let's say that I have a fixed price in mind for each ticket. Let's say each ticket is going to cost, I don't know, 1 Ether. 1 Ether is too much, but we're just doing this as an example. So whenever someone calls this function, the first thing I check is that they're paying the right amount. So I want to check that msg.value, which is the amount that is paid when this function is called, is greater than or equal to the ticket price. And let's say I have my ticket price somewhere. And let's say my ticket price is 1 Ether. Okay. Well, actually, I would check that it's exactly the ticket price, right? I don't want anyone to pay more. So now when someone buys a ticket, I just want to have a record of that. I want to record the address of the person who bought the ticket. So maybe I can just have a mapping. And this mapping basically maps the ticket number to the address of the person who has bought it. So let's just call this player, because I'm going to think of each person as a player here. And let me also keep track of the number of tickets. So I have number of tickets. And here what I would do is simply I increase the number of tickets. And I also say that the player for this particular number is whoever called this function. So MSG doesn't. Okay. Actually, can I close this? So now I have basically a list of all of my players. It's a mapping that maps each ticket's number to the player who has actually paid for it. And anyone can buy as many tickets as they like. So with the same address, you can buy as many tickets as you like. There's no limit on that. And of course, then I want to have another function where I can actually choose one of the players uniformly at random to be the winner of the game. And actually, to be more specific, I'm not going to choose a player as the winner. I'm going to choose a ticket as the winner, right? So if you have more tickets, you should have a higher chance of winning. So let's say I have a function and I'm just going to call this one randomize. And its job is to randomly pick one of the tickets. So I make it public. It doesn't have to be payable. Now, here's the thing. We're going to talk a lot about how this randomize function is going to work, but let's just finish writing the contract and then get back here. So let's say I have another integer here, which is the winning ticket. And basically what this randomize does is that it chooses the winning tickets. Right. I will come back to this later. This is the main topic of today. But let's say that we've called this randomize and the winning ticket is chosen. So I should also have another function that can be called by the winning person to get their money. So maybe I can have a function called collect reward. And this is also public. And let's say that I just require that this collect reward should be called by the person who has the winning ticket. So I have to require that msg.sender, the person who's calling this function, is actually the player corresponding to the winning tickets. Okay, and if this is the case, then I would just pay everything to this particular person. So I can just say, well, we talked about this before. I can use transfer, or I can use send, or I can use call. In this particular case, let's say I want to really simplify my lottery and I want to make sure that contracts cannot take part. Okay, so I will get back to how to do that, but let's say I know for sure that none of my players are contracts, so I can just use transfer. So I would just say, I take an address payable. This is the person who's supposed to receive it, and this will be the player who has the winning tickets. And then I just say receiver the transfer. And now I can either send the entire balance, or I actually know what the balance is. It's the number of tickets times ticket price. So I can just do this, number of tickets times ticket price. I can also say just transfer the entire balance of the current contract. Okay. Of course, generally, whenever I write contracts, I start with writing terrible contracts, and then I tell you what's wrong with them. So you should never write a contract like this. But for now, let's say we have these things. Well, first of all, I don't really need this require anymore, right? Because who cares who calls this function? I'm giving the money to the winner anyway. So even if someone else calls this function, the money is not going to go to the person who called the function. It's going to go to the person who actually won the lottery. So I don't need this require. But I said a point about wanting to make sure that only real people, only external accounts can take part in the contract. And I want to make sure that if you're another contract, you cannot be a player. Because of course, we've seen before what kinds of attacks you can do if you allow other contracts to sign up in your contract. So I can actually enforce this here when the buy ticket function is called. So how do I enforce that buy ticket can only be called by a real person, by an external account, and not by another contract? Well, this goes back to the ideas that we had with global variables. So let's just look at this one more time. Okay. Oh, wrong website. I want probably this one. Okay. So these are some of the global variables that we have. And actually, you can see that we have two different variables. One is called msg.sender, and this is the address of the account that is calling the current function. And it can also be another contract. But then we have something else called tx.origin. And tx.origin is the person who created the transaction. So tx.origin is guaranteed to be an external account, to be a non-contract account. So the way I can make sure that people can call this function directly only and not through another contract is to just say I require that tx.origin is the same as msg.send. So I'm requiring that this function buy ticket is called directly using a transaction by an external account. And it's not called by some other contract. Okay. So this part makes sure that I will not be vulnerable to any of the reentrancy attacks or things like that that we've seen before. So this is good. I check the value. Everything here is nice, it seems. Now, the only problem is this randomize. So first of all, my ticket numbers are basically from 0 to number of tickets minus 1, right? Because that's the way I'm doing it here. So the first time buy ticket is called, I'm setting a player for ticket number 0 and then increasing the number of tickets to 1 and so on. So let's say instead of number of tickets, if I had n, the tickets are numbered from 0 to n minus 1. So now I just want to choose a random number between 0 and n minus 1. How can I do that? Now, let's first talk about what properties we want to have. Well, a really important property that I want to have is that this random number should not be tampered with by anyone in the entire system. So again, as before, I said that we are assuming everyone is a cheater. We're assuming everyone does whatever they can to get any advantage that they can whenever we're writing these contracts. So it has to be trustless. And when I'm generating this random number, I have to be sure that none of the players and also none of the external actors, let's say miners or anyone else, can really affect the outputs. So that's the first property that I need here. I need it to be tamper-proof. And then the second property I need is for this to be really a uniform random number, right? So it's not enough that no one can tamper with it and no one can change it, because I can just return 1 and no one can change that, right? But I also want it to have the right distribution. I want every ticket to have the same probability of winning here. So these are the two things that I want to ensure. Again, as usual, I'm going to start with terrible solutions, and then I'll tell you what's wrong and how we can make it better. So one of the things that people do is that they actually use these global variables in order to generate the random number. So if you look here, there's something called block.timestamp. Okay, and block.timestamp is basically a timestamp on every block. So every block in Ethereum has a time, and this is the time that the miner created the block, and this is Unix standard time. So it's the number of seconds that has passed since January 1, 1970 at 0 UTC. So you can do block.timestamp. So here's what I can do. I can say my winning ticket is just going to be block.timestamp. And of course, I want a number between 0 to n minus 1. So I can just say modulo n. And again, n was number of tickets. Okay. So what are the problems here? Let's just look at this contract. And again, it's a terrible contract right now. Well, one very silly problem here is actually that you can call collect reward before you've even called randomize, right? Because all of these functions are in this contract and all of them are public. So anyone can create any transaction that calls any of these functions at any time. So I can actually call collect reward. And if that happens, that's actually bad, because originally the winning ticket is just 0. So if I want to attack here, I would just buy the first ticket. And that first ticket, ticket number 0, is the winning ticket as long as randomize is not called. And I just wait for others to buy tickets, and then I suddenly call collect reward, and I collect all the money. So the first problem here is the problem of time. Generally, when you write smart contracts, you have to make sure that the functions can only be called in the orders that you have in mind in your protocol. So you probably have the same problem when you're implementing rock, paper, scissors for the homework. You have to make sure that people cannot call your functions in an order that was not desired. So how do I make sure this doesn't happen? Well, I can just have some Boolean here. So let's say I have a Boolean and I call it rand flag, which just tells me whether this randomize has been called or not. So when I call this, I set the rand flag to true. And then for collect reward, I just add a requirement that randomize should have been called before this. Okay. So this makes sure that no one can collect the reward before randomize is called. But now we have another problem here as well, which is kind of funny. You can call randomize more than once, right? So let's say you're just a user on the blockchain, you call randomize, and you see that you're not winning. So you just try again. You create another transaction, call randomize again. We have to make sure That's not possible. So again, here I have to also require that rand flag is false, or I can just write it like this. Okay, great. But we have even more similar problems. So let's say I've called randomize. And well, again, all of these functions are public, so anyone can call them. So let's say I've called randomize, and let's say you are a user somewhere else, and you haven't seen my transaction calling randomize yet. So maybe you're trying to buy a ticket at almost the same time. And then there are two transactions being propagated. One is my transaction that is calling randomize, and the other one is your transaction, which is just trying to buy a ticket. And maybe the miners put my transaction first. So actually the problem is that even after randomize is called, you might have a situation where someone is calling buy tickets. And of course, they're not going to win, right? Because this randomize is going to choose one of the tickets that was there before it was called. And so if you buy a ticket after randomize is called, you're just giving free money out and you're not getting anything. And actually the attack here would be that if randomize is called and you're the person winning this entire thing, you would not call collect reward. You would just wait to see if there are any unlucky people who buy tickets after randomize is called, right? Because in that case, the winner is actually going to get all the money in the end. So I actually have to, again, take this flag. Maybe let me put it here. And when I'm calling buy ticket, I have to also require that randomize is not called. Okay. But we have still more problems here because right now it seems like anyone can call randomize at any time. So maybe I want to make sure that randomize can only be called after a certain number of tickets are solved, right? Or maybe I want to make sure that randomize is called after a specific amount of time. So how can I do that? Well, again, I can actually look at this block.timestamp. So I can use this block.timestamp in my functions to enforce some sort of timing. So maybe I can say that buy tickets can be called between this time, and then randomize can be called between another pair of times, and so on. But okay, these are all the small problems around this, but let's get actually to the main problem here. The main problem here is that you're using block.timestamp as a source of randomness. And normally block.timestamp should be kind of random if you think about it, because, well, if I'm a miner and I'm just solving this proof of work, or actually Ethereum has already gone to proof of stake, but let's say we're talking about proof of work here. So if I'm just solving this proof of work problem, trying to add my block, I don't really know when it will be solved. So it might be that my timestamp actually is random. But the problem again is that we are giving too much control to the miners. So what happens if the miner is also a player in this system? And especially what happens if the miner is really rich, and let's say the miner is buying half of all the tickets in your lottery, or maybe the miner is buying 1/3 of all the tickets in your lottery. So the miner actually gets to choose block.timestamp. Now, they don't get to choose it as they wish, because of course, if you add a block, the timestamp of the current block should be more than the timestamp of the previous block. And there are some small checks like that. But generally, there is no way for anyone to find out if you just lie about your timestamp a little bit. So maybe you find the right block at, let's say, right now at this particular time, and then you set the timestamp to 1 second before or 1 second after. Okay, that can be enough for you to actually get an advantage here and then win this randomize. And this happens, of course, if the miner is taking part. So block.timestamp is a terrible idea. You should never use it as a source of randomness because it's basically controlled by the miners. So what this means is that the miner who's adding the call to the function randomize can basically pick the winner to some extent. It can affect the result here. It's not tamper-proof. And if that miner also has a lot of stake, if that miner has a lot of the tickets, then there's a good chance that they can make themselves. Okay. So what else can I do? Well, let's look here. We have some other things that we can also use. So maybe I can use block hash, right? So that's much harder to control. So instead of taking block.timestamp, I take the block hash of the current block. I have to give it the block number, so I have to write it like this. So I take the hash of the current block, and I say I use that as my random number. Right? And then I just take it modulo the number of tickets. Now, this is a little bit better than just using the timestamp, but again, it has the same problem, right? Even though the miner cannot directly choose the block hash, the miner can still tamper with it. So if I'm a miner and I also have a stake here, if I've bought a lot of the tickets, when I'm mining this call to randomize, I can check if my block hash would make it so that I win here or so that I lose. And again, let's say that I have half of all the tickets. So that's the extreme case. If I'm the miner and I have half of the tickets, what I can do is to just change the block a little bit. Maybe I again change the timestamp, and that would change the hash entirely, right? And then I can just try many different values, kind of like proof of work, but with a much lower threshold. I just try different values of timestamp, or I just make small changes in my block so that the hash changes a lot. And then I just get more chances of actually winning this lottery. So again, even though the miner doesn't control block hash exactly, the miner can actually tamper with the block hash. And that's enough for this to not be a good enough solution for random number generation. So I cannot have something like this. Again, this would ensure that the miner wins. Okay. What else can I do? So how can I really get a random number? Well, maybe I can say, let's make sure this is not under the control of the current miner. Maybe I do something like this. So let's take the hash of the previous block instead of the hash of the current block. Right? So the miner who's adding the current block, they have no control over what the hash of the previous block is. But again, the problem is that the miner can control a lot of things here because, well, if the miner sees that they're losing, they will just not add the call to randomize to the current block. Right? They always have the choice of not including your transaction and just letting someone else take care of it in the future blocks. And also, even forget about the miners. Let's say that all the miners are honest and they're just doing their job. Some malicious player who's just looking at the blockchain can keep track of the hash of all the blocks. And as soon as they see that a block is added that has a good hash, a hash that would make them win the lottery, they will call the randomize function so that it's added to the next block. Okay, so you see, no matter what you do, there's no way around this. You cannot use any of these global variables or variables used by miners or saved on the blockchain to actually generate a random number. So never do this. Okay. What else can I do? Well, one thing I can do is I can actually ask the players themselves to help me with the generation of the random number. So maybe I can say that every time a player buys a ticket, they have to also give me some random number. And then at the end, I will just sum up all the random numbers that are given to me by all the players. And I take that modulo n, and I say that's the winning tickets. Okay, pretty easy. So let's say here, when you buy a ticket, you have to give some number, let's call it x. And actually, let me put it as uint. And let's say that I also save the x amounts. So I use big X to save all the X. So I say X of number of tickets is X. So every player just gives me some number X, and I save all of these numbers X. And then here, instead of saying that my winning ticket is this thing, I just say, let's take the sum of all the numbers that were given to me by all the players, and let's take that modulo n. So let's say I have a sum, and for I from 0 to number of tickets, I just increase sum by xi, and then I just say the winning ticket is sum modulo n, modulo number of tickets. Okay. You might think this is making things better because now the miners have no control, right? So you just have to care about the players and what kind of sketchy things the players can do. But actually, we have a lot of problems here. So what kind of attack can I do? Okay, let me add something else. Let's say that I want this, let's say I want to have exactly, I don't know, 1,000 players. So here, let's say I require that the number of tickets is less than 1,000. And here, when the randomize is called, I'm going to require that there are exactly 1,000 tickets. I can have 1,000,000 or 1,000 or whatever. Let's say I have exactly 1,000 tickets. Okay. So who wins the lottery in this case? Just give me a guess. And again, the important point here is that we are assuming everyone is rational in a game theoretic sense. So we're assuming that everyone just wants to maximize their own payoff, their own money that they get out of this contract. Okay. So in this case, actually, always it's always the last player who wins, right? Because we know that we're going to take the sum of all the numbers provided by all the players and take that modulo the number of players, right? So the last player can always choose their value of X so that the sum modulo the number of players becomes their number, right? So the last player can always win. And that's not great. Now, of course, this was the case when I had exactly 1,000 players. So the player with number 999 could always win. But let me remove this, and let's say that I can have any number of players. Now who wins? Again, the last player always wins, right? Because if you're player 1, you would choose your X so that the sum of all the X values modulo the number of players becomes your number. And then if you're player 2, you do the same thing again. And this goes on forever. So this is just a very, really stupid contract. And the competition here is to figure out who's going to be the last person to buy a ticket, because the last person is always going to win the lot. Okay. So that's, of course, a problem. But we actually have an even bigger problem. Can you see another problem in this contract? Okay, so in the previous sessions, I actually talked about gas, right? So whenever you call a function, you have to pay some money for the gas, and the amount of gas that it uses is proportional to the amount of computation that it does. And in this case, our randomized function has a for loop in it. And this for loop, actually, I should use uint. This for loop is going from 0 to n. Now, what happens if the number of players is really large? So what happens if my contract is really popular and let's say 1 million people took part in my lottery? Then this function will use a lot of gas. And since this function uses a lot of gas, no one wants to actually call it, right? Because, well, we just said this function is public, anyone can call it, and we're not doing any access control. The idea was that someone will eventually call it, right? But if it costs so much to call, no one would call it. Now, you can, of course, say that, well, I can just run this contract, run this function on my own machine and figure out if I'm going to be the winner. And then if I'm the winner, as the winner, I have an incentive to actually call randomize and pay for the gas, right? Because even though it uses a lot of gas, at the end of it, if I know that I will win, I can then collect my reward, and that's great. So we can always say that the winner will definitely call randomize, right? But we have another problem, and the problem is, again, with the amount of gas that this thing is using. So in Ethereum, we have a limit on the amount of gas that each block can use. So let me just Google this again. Ethereum block gas limits. Okay. I cannot find it again, but okay. Here it is on Stack Exchange. So there is some maximum amount of gas that each block can use. I think it's something like 30 million units of gas. So that means that if this particular function uses more than the block gas limit, then it can never be called successfully, right? So whenever you call a function, you can give it at most 30 million units of gas. And if the number of tickets sold is so much that whenever I call this function, it needs more than 30 million units, then I will always run out of gas. Yes?
What's the reason for the gas maximum?
Oh, that's because we have a new block coming in every, let's say, 13 seconds. And we want everyone on the network to be able to keep up, right? So if I can have a block that has a lot of computation, then maybe some of the nodes on the network cannot do it in time, and then they will not be able to follow along with the blockchain. So I have 30 million units of gas. This function uses more than 30 million. So anyone who ever calls this function will get an out of gas exception. And if that happens, that basically means this function is not callable, right? Because I call it, I run out of gas, and we've talked about this before. If you run out of gas, the entire transaction is reverted. So it's just as if you haven't called it, except that you lose your gas money as well. So this basically means that because there is this costly for loop inside this function, this entire functionality is disabled. No one can really use it anymore, which means everyone's money is going to be locked in the contracts. So when I said we have a problem worse than the last person always winning, this is the problem. Like, no one wins, all the money is locked. Okay, so what should we do? Well, generally, my advice is to never use any kind of loop in your smart contracts. Don't use a for loop, don't use a while loop, don't use anything that can spend more than like a constant amount of gas. Now, there is nothing in the language that stops you from using a for loop, but it's just a bad idea. So I have to make sure that this sum is calculated in a different way. So maybe I can just put this sum up here as well. And then when I save this x, I say add the sum here. Okay, add x to the sum here. So now this function is going to take a constant amount of gas, O1. And then when I'm doing the randomize, I just do this, and this is again O1. So very important to make sure that all of your functions run in O1. Okay, now I don't have the gas problem. I still have the problem that the last player always wins. Okay. And of course, I also have the problem that anyone can call randomize at any time. So maybe to avoid that one, I can say that here I can require block.number to be larger than some fixed number. Okay, so I want to make sure that there is enough time for people to buy tickets, and then the randomize function can only be called after a particular block number. So that's good, but I'm actually going to comment this out because I cannot use the block.number here in Remix. But let's say I don't have a timing problem. Let's say I've made sure that all of my functions can only be called at the right times. Now my problem is that the last person is always winning. So how do I solve this? This is actually very similar to the problem we had with rock, paper, scissors, right? So when we were talking about a protocol to play rock, paper, scissors, there were two players. And if one player could see what the other player is going to play, then they could choose their own strategy so that they always win. And it's something very similar here. Instead that we don't have just two players, we have any number of players. So if you're the last player and you see what values of X the previous players have given, then you can always win. So the way to avoid this is to hide those values. And of course, the way we hide them is using a hash function. We use a commitment scheme. Okay. So now I say that when you buy your ticket, you're not going to actually give me your value X. You're going to give me the hash of X. Right. And I'm going to save that. So instead of saving X values, I'm going to have a mapping called H, which basically saves the hash values. Let's go with lowercase h. So, oh, no, okay. Let's do the same thing. Let's go with uppercase h. And here, when you buy a ticket, you give me an integer h. And this h is supposed to be the hash. So I would just say, let's save this hash. Okay. And actually, in Solidity, I have a bunch of hash functions that I can use. These are some of the hash functions that I have. So for example, I can use SHA-256. So let's say I always use SHA-256. I have to be careful about the types here. So a SHA-256 actually doesn't return a uint, it returns a bytes 32 or whatever. But again, in my codes, I'm just too lazy to convert the types. Just be careful when you're writing your own code to convert the types, otherwise you will get a compiler. So anyway, a person who buys a ticket is going to give me the hash of their number, not the number itself. So I cannot add anything to the sum here because I don't have the actual numbers. And then let's say that I have another function. And this function is called, let's say, reveal. And the idea here is that, well, after everyone has bought their tickets, I just want to do reveal and show what my actual number X was. So I'm going to open my hash. I'm going to reveal my commitment. Again, for each of these, I'm going to have some requirements on time. So maybe here I say require that block.number is greater than or equal to something, and it's less than or equal to something else. I will have the same kind of requirements here in reveal, in randomize, and in collect reward. And of course, I choose these numbers so that they just make sense, right? So I want to make sure that I first give some time for everyone to buy their tickets. Then I give some time for everyone to do the reveal. Then I give them time to call randomize. And then finally, I give some time to the last person, to the winner to call collect reward. And actually here, I don't need this part, right? So I don't need to have a deadline for the winner to collect the reward. It's fine. Okay, so generally this is very common. And a lot of the time, what you see in contracts is that these limits are actually set by the constructor function. So maybe I have some time limits here. So I have maybe, let's say, some T1, T2, T3, whatever. And then I have my constructor, and this constructor actually sets the values for this. So maybe I can say that T1 is current block number, so the time that the contract was deployed, plus let's say 1,000. And then here in buy ticket, I say require the block number to be at most T1. So I say from the time that I deploy the contract, you have 1,000 blocks of time to buy a ticket. And then I can do the same thing for T2, T3, so on. I'm just too lazy to do that. And then I'll check the times here. Okay, but let's just talk about this function reveal now. So I have a hash that I've given here. So when I reveal, I have to give several things. I have to give my ticket number, right? So which ticket am I revealing for? And I have to give my value of X. Now, what should this function do? It has to first check that I'm really giving an X with the right hash, right? So I will require that the hash of X is the right value. And again, the hash function was this. So I would require that the SHA-256 of X is actually equal to the hash that was given to me for that particular ticket number. Okay, and if this is done, then I add X to myself. Okay. Show me another attack. What's wrong here? So everyone is first committing to their values and then they're revealing. So just give me another attack that you can do. Again, this is very subtle. And actually, I'm going to tell you already that your final exam will contain some examples of problems like this, where I give you a contract and I say, find an attack. So it seems everything is fine because, of course, when you're buying the ticket, you're committing to a hash value without knowing any of the values of the other people. And when you're revealing, you also don't know. So yeah, the subtle problem here is that you can reveal several times, right? So if I just call the function reveal several times, my value X gets added to the sum several times. So I have to also make sure that doesn't happen. So I have to keep track of all the values that have been revealed and make sure that no one is revealing more than once. So I will have something like this. Maybe I have another mapping that maps unsigned integers to Booleans. And let's call this R, which basically checks whether something is revealed. And by the way, don't use names like this, use descriptive names. I'm just lazy. So here, when you do reveal, you have to set the R of the ticket number to true. And of course, here you have to require that the R of the ticket number is false. And actually, without this, we had an even bigger problem. So imagine that you reveal once, then I can have something like front running. I can know what your value was, and I could just call the reveal for you, because the reveal is not really checking that you are the person who owns this ticket. Anyone can reveal, right? But the idea is that only you know the right value of this. Okay, now I seem to finally have a working solution. But let's go back and actually see. So I said that I want my randomization to have two nice properties. I wanted to make sure that no one can tamper with it. And I also wanted to make sure that it has the right distribution. Now you can already see that I don't have the second property here because there is nothing random here, right? So I'm just getting a bunch of numbers from people and I'm just adding them up and taking it modulo n. So there isn't nothing really random. But the point here is that even if one person is honest and plays uniformly at random, even if one of the X values that is given to you is really chosen uniformly at random, then the entire solution, the entire sum will also be uniformly distributed. So I have a very good guarantee of uniform randomness here, and the guarantee is that even if one person is honest, my final solution will have the right distribution, right? So this is very different from the kind of guarantees that we're used to. For example, the Bitcoin guarantee was that if half of the computational power is honest, then we will have consensus and everything. But here it's just that I need one honest person. I just need one person who honestly chooses this value of X uniformly at random and then hashes it when they're buying their tickets. And then the entire result would be uniform. Okay. But again, give me another attack. We have some more problems here. And actually, don't look at the code this time. This is not just a problem of the way we've coded it this time. We have a problem with the entire protocol. So I talked about what happens if someone calls reveal several times, and we now have some sort of defense against that. But what if someone never calls reveal? Right? If you don't call reveal, your value of X is not getting added to the sum. Now, why would you want to do that? Let's say you're a really rich person and you have bought half of the tickets. Let's say you own all the tickets with an even number, right? And let's say you've chosen one of your values X to just be 1, right? So you just wait for everyone else to reveal and you look at the current value of sum. And then you think, would it be good for me to reveal this last ticket that I have, this last value of X that I have or not? And actually, it's like if you own half of the tickets, you can basically win with probability 1. So we have a problem like this. We have a problem that it might be in someone's best interest not to reveal. So what can we do? How can we make sure that everyone has to reveal? Well, one very useless thing that we can do is to say that if you don't reveal, you will not ever win. So we can say that when I'm doing this randomization here, I'm not going to take it modulo the number of all the tickets that were bought. I'm going to take it modulo the number of tickets that actually did the revelation part correctly, right? But that's not going to help too much because again, if I own half of the tickets, I don't care if I lose one of my chances, if I can change the random number and actually win the entire lottery, right? So that's not going to help. What else can I do? I can say that if you don't reveal, well, I can just say if someone doesn't reveal, then I know for sure that they're trying to tamper with my random number. So I would just cancel the lottery and run it again. So even if one person does not reveal, I cancel it, and then I just have to do another lottery. Now, in that case, what can I do with the money? Well, the problem is that even though I have everyone's money in this contract and I can refund everyone, they've already also paid for gas, right? So every time that someone has called buy ticket, for example, they've paid the gas for execution of this code. So if I just say, okay, the lottery is canceled and I'm going to give your money back to you, that's not really enough because the gas money is already gone. So another idea can be, okay, if you don't reveal, I will not give you your money back, but I will use that money to instead pay the other people for their gas costs. So let's say whenever someone is dishonest, we just take their money and we don't refund their deposits. Instead, we divide it evenly among others. But then again, this creates a situation where you don't get penalized enough if you have a lot of tickets, right? So again, if I have half of all the tickets and I don't reveal one of them, I'm still getting half of my money back, right? And also, even doing the lottery again is not going to solve our problem because, again, constantly think about the case of rich people. Let's say I own half of all the tickets. And let's say I look at the way that other people are revealing, I just keep track of the value of the sum, and I see that I was unlucky and I'm not winning the lottery. So I can just decide not to reveal one of my tickets. I lose the deposit of one of my tickets, but then the lottery has to run again. And then when we run it again, I have a 50% chance of winning it. So if I have a huge stake in this lottery, it actually makes sense for me not to reveal in that case and make the lottery basically canceled and force it to be done again. So yeah, we have all of these problems. One solution here can be to just require a really huge deposit from each of the players. So maybe I can say that my lottery accepts, let's say, 100 players. And I can say every time that you sign up, you have to give 1 Ether for the lottery. And then you have to put down a deposit of 200 Ether. And I will confiscate your deposit if you don't reveal. And that would really disincentivize any kind of dishonest behavior. But then, of course, the problem is that you need huge deposits. So yeah, I'm sorry to finish this lecture on this low, but there's really nothing we can do here. I will give you some partially better solutions next time. We can actually use something called secret sharing. But generally, in the real world, all the lottery contracts on the blockchain have either been fraudulent or they've gone bankrupt because no one uses them. Okay, great. I'll see you next week.